Hi, welcome to another lecture on Calculus 2. Today's topic is cyclic integration by parts and reduction. We have several examples here that I've noted. These examples are going to show up later on again in the context of trigonometric integrations and their powers. Uh, However, we are going to just look at the simpler case today, which is a single trig function like sine, just cosine, or just secant. In the next section, we are going to see the products of some of these. For example, sine times cosine, or secant times tangent, and so on. Other than that, there's also two types of ideas being presented here. One is cyclic integration by parts, sometimes I refer to as self-referral or self-referential. That means when we are starting with a integral of something, during the process of integration by parts, we are going to see exactly the same integral again. And that helps us to calculate it. I'm going to explain in detail as we go through. The idea of reduction, it refers to the fact that you see a certain power on the left and you see a smaller power on the right, indicating that the problem has been made simpler by going to a lower power. The first three examples that we have here exhibit both the cyclic aspect and the reduction aspect. This example here, it just has the reduction. Now, as we go through the calculation, you are going to become more familiar with what I just said in terms of both what is it that is cyclic and what does it mean to do a reduction. Okay, let's start with the first example, which is power of sine, and so I'm going to start with integral of sine to some power. Now this power, so long as it is a fixed number, it's okay for us. The sine to the power of n of x dx. We might call it I for the integral I'm trying to calculate, so that if I have to write it again, I have an abbreviation for it. Well, how does integration by parts help here? What is our u and what's our dv? You remember dv should be such that integrating it will be easy. So we are just applying that basic formula. This is really a practice on u dv being equal to u times v minus integral of v times du. And the question is how to choose u and v. So dv, a suggestion that comes through looking at this, will be just sine of x dx, because that is something that I can easily integrate and find what the v is. Well, what is going to be left for u? Well, u is going to be left, if I remove a sine, I'm just left with sine to power n minus 1 of x. Well, on the other side, I need the du and I need the v itself. So du is easy. I differentiate this thing, exponent times 1 less power times the derivative of the base, which is cosine of x. How about v? V is a function whose derivative is sine. Well, that is going to be minus cosine of x. So we start with these, and then the integral I want to calculate then is going to be, that integral is u times v. So u times v, I write minus cosine of x first, sine of n minus 1 of x, minus integral of v du. So v is minus cosine of x, du, I forgot to put my dx here, sorry. this is v times du. Du is going to be n minus 1 sine to power of n minus 2 cosine of x dx. We notice that we can simplify a bit, so minus cosine of x sine to power of n minus 1 of x minus n minus 1, they can be all condensed into a factor of n minus 1 outside of the integral, cosine and times cosine. I can write it as cosine square of x dx. Next, I will have minus cosine of x sine to power of n minus 1 of x plus n minus 1. Now we apply a basic trig identity in all these examples, which is, well, cosine square of x is 1 minus sine square of x. So this is going to be sine to power of n minus 2 times 1 minus sine square, and then dx. Now what I'm going to do is to multiply through, before we get down in all the details, what is going to come out. There's going to be sine to power of n minus 2 when I multiply by 1. And when I multiply this one with sine square, I'll get sine to power of n. And that is what we mean by cyclic. We were calculating sine to power of n. Same sine to power of n shows up on the right hand side. When you are seeing the same thing again, when this calculation goes back to itself, we call that cyclic or self-referential or self-referral. Some people call it deja vu, or whatever terminology. Some people call it circular. So all sorts of terminology is used for this approach that we are using. This approach leads us to a situation where whatever we are calculating shows up on the right hand side again. So let's go ahead and do it. So I'll have first piece just stays as it is, cosine x sine to power of n minus 1 of x plus n minus 1. Multiplying this by just 1 is going to be sine to power of n minus 2 of x dx. So I split this into two integrals, and multiplying by sine square. Now I remember there's a minus here, and there's factor of n minus 1 over there, n minus 1 minus times integral of product of these two is sine to power of n of x dx. Now let's remember this I that we were writing there is I is just the integral sine to power of n of x dx. Now what I do is that take this that are cyclic component or self-referential component or whatever you want to call it, that's the same thing, or deja vu component, I bring it to the left hand side. So n minus 1 sine to power of n of x dx, and I'm left with everything else on the right hand side, minus cosine of x sine to power of n minus 1 of x and plus n minus 1 integral of sine to power of n minus 2 of x dx. Well, how do we add these two? I have 1 of something, so I have 1 of this thing, and n minus 1 of the same thing. When you add it, 1 plus n minus 1 just becomes n integral of sine to power of n of x dx is equal to minus cosine of x sine to power of n minus 1 of x, and then n minus 1 integral of sine to power of n minus 2 of x dx. Well, all that is left to do is just divide by an n. So we recovering our integral sine to power of n of x dx is equal to, so dividing by n, it's minus 1 over n cosine of x sine to power of n minus 1 over x plus n minus 1 over n integral of sine to power of n minus 2 of x dx. So what happened? We saw the cyclic manifestation. The same integral showed up on the right hand side. We take it to the left and combine, and we achieved reduction, meaning the power from n went down to n minus 2, and that is an example of the topic for today, that you have cyclic computation plus a reduction. Okay, and now well, this was one of the three things we are going to show here. So we showed item 1 here. Item 2 is very similar to that. Let me leave that to you, that you repeat the argument and check your answer against what we have here. And then number 3 is a little bit more interesting. But before doing that, let's do an example of what we just achieved, put it to some use in the context of some concrete calculation, and see how we make use of this reduction. So one of the type of examples that shows up in this section quite often is a definite integral, for example, between 0 and pi over 2. The limits of integral chosen to be nice with respect to what we want to do, and some powers of sine. As you do this thing, you notice that it makes it a bit of a difference if you have even power or odd power, but let's do one of them and see what happens. So suppose I choose power 10, sine to power 10 of x. Again, as I mentioned, this topic that we are doing today here is going to show up in the next section again, with slightly different title, but very similar ideas, perhaps a bit more complicated. At any rate, so all that has happened here is that my integral is definite from 0 to pi over 2, and my n is specified. The n that I have here is supposed to be 10. So let's just go ahead and use this formula that we have, put it between the limits of 0 and pi over 2, and also specify what n is supposed to be. So minus 1 over n is 10, remember. Cosine of x, sine to power of, well, what power is it going to be? Well, 10 minus 1 is 9 of x. And then again, 10 minus 1 is 9 over 10. Integral, same limits here, 0 to pi over 2. Sine to power of, whatever we had, go down 2 steps, 8 of x dx. And don't forget that this expression here is to be calculated between the same limits, 0 and pi over 2. Well, hopefully some simplification shows up here, otherwise it's going to be a nightmare. So cosine of pi over 2, well, that is conveniently 0, and sine of 0 is 0. So at both ends, this expression here just falls out. It just becomes conveniently 0. This whole thing becomes 0 because at the top end the cosine is 0, at the bottom end sine is 0, and thankfully it just goes away. That reduces the clutter. So 0 to pi over 2 sine to power of 10 of x dx becomes slightly simpler. Becomes that integral to power of 8. Okay, so we noticed that we went from power 10 to power 8 at the expense of multiplying by that number minus 1 over that number. Well, The problem is just relegated from what it was to something slightly simpler. So we are going to go ahead and struggle against that one. So pi over 2 again, sine to power of 8 of x dx. What do you think that is going to be? Would you like to just pause it for a second and try two ways, perhaps guess straight out based on what we did, or just go back and repeat the argument just like we did? Like that's the formula here. Now you're using power 8. This one, so long as both terms are there, is going to vanish just like it vanished here. And then n minus 1 over n, what's that going to be? If this is 8, that's going to be what? 7/8, and that's going to become 6. Okay, so, or just follow the reasoning here. 10 became 9/10, so 8 is going to become 7/8, and integral of 0 to pi over 2 of sine to power of 6 of x dx. Now we see the trend, so just continue that style. So sine to power of 6 of x. Again, I invite you to pause this thing and calculate it two ways and see what you come down to. Okay, so pause it and come back. So I'll have 5/6 of this to power of 4 of x dx, and again sine to power of 4 of x dx is going to be 3/4 of integral 0 to pi over 2 of sine square of x dx. Now sine square, you have seen it multiple times, or we can still go down this road. Sine square, if this is 2, my cosine is there, this becomes sine to power of 1. This is 1 over 2. This is sine to power of 0. End of the road. Sine to power of 0, anything to power of 0 is just 1. You're integrating 1. Well, that's the light at the end of a tunnel. It stops somewhere, thankfully. It stops here. So let's just continue using this. Of course, you could use double angle formulas as well. Many different ways of doing the same thing. This is 1/2 of integral of 0 to power of pi over 2. So we went from 10, 8, 6, 4, 2, 0. And well, that's 1/2 of integral of 0 to pi over 2 of 1 dx. Integral of 1 is just x. So 1/2 of x between 0 and pi over 2. Well, this pi over 2 times 1/2. 1/2 of pi over 2. Well, I just found this, so let me just put it back. This is 3/4 of 1/2 of pi over 2. Well, that means I got this. Sine to power of 4, I got it. So that's 5/6 of 3/4 of 1/2 of pi over 2. You get a hang of it? By the time you come here, 7/8 of sine to power 6 we just did. So 5/6 of 3/4 of 1/2 of pi over 2. And here's our holy grail. We wanted to calculate this one. 9/10 of 7/8 of 5/6 of 3/4 of 1/2 of pi over 2. Of course, standard pattern here. You see 9, 7, 5, 3, 1. Denominator 10, 8, 6, 4, 2. and at the end there is a pi over 2 hanging next to all of these things. So that gives us idea that if I have a power here, we practice for a even power. For even power, I have a formula that says start with from that even power, go down in steps of 2, and start from 1 less than that and just go down on them as well, steps of 2. At the end, multiply by pi over 2. So we have a kind of hand waving proof as to what would be sine to power of n of x dx in case n is even. Can you think what will happen when n is odd? But let's do n even. N even, start with n minus 1 over n. Go down 2 on the numerator, go down 2 on the denominator, so on. Keep going until you hit 1/2, and then another factor of pi half comes at the end. So we have one of these formulas that connects pi to a trigonometric integral. Okay, so that was an example of how to make use of some of these formulas. So we calculated sine to power of 10, integral of sine to power of 10 between 0 and pi over 2, and that is what we got. Now those of you who are interested in this type of mathematics, you can use factorials. You can use factorials to create concise formulas for the right hand side, but that goes a little bit beyond what we are interested in right now. It's quite easy. Just factor 2 from all of these things. You see 5, 4, 3, 2, 1. So that's easy factorial. Numerator, you have to apply a bit of a trick to force it to be factorial. There's nothing to factor here. So you have to fill in the detail, meaning multiply by the missing numbers. 10, 8, 6, 4, 2. That becomes 10 factorial. Divide by what you multiplied with, which is going to be like what you had in the denominator, and then clean it up. If you're interested, let me know. So let's move on to something else. So problem 2, do at home. Well, do it yourself. Problem 3, a bit more convoluted, is the issue of what happens if I have secant to power of n of x dx. And again, we said in the next section you're going to see this a bit more mixed up with secant tangent in the same place. Okay. For secant, might be a good idea for us to refresh our memory about some differentiation rules so that we can refer to them later on, which is, well, what's the derivative of secant of x anyway? Let's to get ready for integration by parts, we need some of these things. So secant, you remember derivative is secant of x, tangent of x. Since we are dealing with powers, let's just practice the power as well. Secant to power of n of x dx. What if I want to differentiate that? Well, the exponent comes in, 1 less than the exponent will be there, and derivative of the base, well, that's what we practice here. Derivative of base is secant of x tangent of x, which simplifies to n secant to power of n of x tangent of x. Another thing that plays a role here is derivative of tangent. What was derivative of tangent? That was, of course, from calculus 1, secant square of x. And as usual, we need a trigonometric identity for these functions. If you remember, tangent square of x, trig identity said what? That this is secant square of x minus 1. So have these things on the side. We are going to refer to them. Okay, we want to do integration by parts. So we have to split this into pieces. One of these pieces has to be easy to integrate. Well, secant by itself is not so friendly, but secant square is. Secant square, if I integrate it, I get tangent. So that gives me an idea to break this thing in the following way, instead of the way we did with the sine or cosine, where we separate the one power. Here we're going to separate two of them. Okay, so that is the reason, motivation for this thing is to do that. Okay, now, well, this was x, of course. This, I'm going to take this thing to be my u and this one to be my dv, because I have a bit of a hope that I can integrate this thing. So I write u to be secant to the power of n minus 2 of x, and dv to be secant square of x dx. Well, for my integration by parts, I need du and I need v. Du, well, sorry. Here we learn how to differentiate a power of secant. That power times the same function times tangent. So my power now is n minus 2. Here was written as n, but here now is n minus 2. So n minus 2 secant n minus 2 tangent of x, and then dx. My v, what's the antiderivative of secant square? Well, that's tan. Okay, so this integral that we are calculating here, that same integral is going to be u times v, so secant to the power of n minus 2 of x tangent of x minus v du. V first, tan of x, n minus 2 secant to the power of n minus 2 of x tan x, then dx. Let's clean up. Secant to the power of n minus 2 of x tan x minus, put the n minus 2 outside, tan x, another tan x makes my tangent square of x, secant to the power of n minus 2 of x dx. One more round, secant n minus 2 of x tan x minus n minus 2 of. Now comes our identity. Instead of tan, I write secant square of x minus 1, and then secant to the power of n minus 2 of x dx. Again, now we see the light at the end of the tunnel, that when I multiply this with that, I get my secant to the power of n back. And that's the cyclic or self-referral or self-referential or circular or deja vu aspect of this. Everybody has a different name for it. And some people say don't give it a name. Tangent of x minus n minus 2. I write secant to power of this times that is n minus 2 minus times another minus makes it a plus, n minus 2, 1 times that is just secant to the power of n minus 2 of x dx. Now remember, this integral was secant to the power of n. So when I the deja vu component of it is that this is same as what you want to calculate. So I bring it to the left, secant to power of n of x dx plus, okay, when it comes on this side it was minus here, now it's plus n minus 2 of the same thing. That's the magic that makes it work, that we went back to what we had, and now I write whatever else is left on the right hand side as it was. This expression, I have it here, and then n minus 2 of integral of secant to power of n minus 2 of x dx. Well, this is one of this and n minus 2 of the same thing, so it becomes n minus 1 of that thing. N minus 1, so 1 plus n minus 2 is n minus 1. Right hand side, you're just writing over and over again. You probably can create a bit of a shortcut and not write as much. Secant to power of n minus 2 of x dx. Well, now I just divide by n minus 1. So I have 1, this is dx, 1 over n minus 1. Let me write my simple function first, so it just looks like everything else I wrote. N minus 2 of x plus n minus 2 over n minus 1 of integral of secant to power of n minus 2 of x dx. And then that is what we were trying to show. Can we make a cute example like we had for sine? Well, I don't see how, because secant never becomes 0. That's a unfortunate thing. So that's our formula. What else did we promise we want to show? So we did number 3. For tangent, something similar shows up, but it's not quite the same. So problem number 4 is, what's the integral of tangent to power of n of x dx? And okay, let's just review a bunch of basic facts about tangent, just like what we did for secant, so that we have easy time of referring to them. So remember, first of all, the trig identity that we have is tangent square is secant square minus 1. That's item number 1. And the tangent of x, of course, the derivative of it is secant square of x. And if I have tangent to some power, let's call it power p, and I want to differentiate it, what happens? Well, of course, I will have power coming in front, tangent to 1 less than the old power, and then derivative of the base, which was secant square of x. And just to rearrange this thing, if I put the p on the left hand side, 1 over p of the derivative of tangent to power of p of x, then is just tangent to power of p minus 1 secant square. We're going to make use of some of these things. Again, we want to apply integration by parts, and this one doesn't have that deja vu. Let's see what happens. First of all, what do I separate? Well, if I separate tan square, I'll have secant squared minus 1, and that at least secant square is a derivative of something I'm well familiar with. So I write this thing as tangent to power of n minus 2 of x, then tangent square of x dx. Now I go ahead and say, well, tan square is secant square minus 1. Now, let me make more room here. Separate it into two integrals, tan n minus 2 secant square dx, and then tan square of x dx. Well, excuse me, tan to the power of n minus 2 of x dx. That is our reduction. We went from n to n minus 2. How about this? I have tangent to some power times secant square. What's the antiderivative of that? I have to increase the power by 1 and just divide by that. So I increase this by 1. It becomes n minus 1. So I'll get tangent to power of n minus 1 of x over n minus 1. And then here I have tangent to power of n minus 2 of x dx. So this power might be read a bit incorrectly. Let me write it better. So that's the power n minus 2. Well, that's it. The problem is finished. The tricky part is the following, that if I have tangent to some power secant square, antiderivative of that is obtained by increasing the power by 1 and just dividing by that. Yeah, that's it. So that's the last formula we were promising, tangent to power of n of x. Again, in the next section, you're going to see a bit more mixed up with the products of tangent and secant at the same time, or sine and a cosine at the same time, and a variety of combination of these things. So we went through cyclic integration, we went through reduction, and we also mentioned that in the next section we are going to see more of the same. Over there we'll see sine times cosine, or secant times tangent, and some variation of that type. Okay, until next time, good luck and God bless.